Okay, so section 4.5 is an introduction to functions and function notation. So we're going to be determining whether a relation is a function or not, using the vertical line test to determine whether a graph represents a function, and then also looking at function notation and how to use function notation. So we're going to start with the definition of a relation, and the word relation sounds like relationship. A relation is a correspondence between two sets where each element in the first set, called the domain, corresponds to at least one element in the second set, called the range. This sounds kind of complicated, but we have actually been dealing with relations all year. So thinking back to like Barbie Bungee, where you guys collected data where you were adding rubber bands to Barbie's bungee cord and looking at the effect on the number of rubber bands to Barbie's drop distance, right? There was a relationship that you guys found, a linear relationship specifically, between the number of rubber bands used for the bungee cord and Barbie's drop distance. And for each cord length, bungee cord length, right? So, for example, for when Barbie's cord was 3 rubber bands, you guys did 3 different drops and measured the drops. Now, the drops weren't necessarily the same distance for each of those 3 drops, but then you guys averaged them and used the averages. But we can say that the first set in that example for Barbie Bungee, which we can refer to as the domain, was the number of rubber bands on Barbie's bungee cord, and the range we could say was all the drop distances in centimeters. Okay, so let me use a different color. Like 0 rubber bands, remember, corresponded to Barbie's height. So I don't remember how much that was. Let's just say it was, 21 centimeters. Okay. And then if you added 1 rubber band, she could have dropped, let's say 23 centimeters, maybe also 23.5 centimeters. Okay. And let's skip ahead a little bit. For 4 rubber bands, she could have dropped, 30 centimeters, and then maybe also 31 centimeters, right? But this first set of numbers would represent the number of rubber bands that were tested. And that set we would refer to as the domain. And then the second set is all of the drop distances, and that set we refer to as the range. Now, each number of rubber bands end up corresponding to at least 1 drop distance. It could have corresponded different drop distances because you did test each number of rubber bands 3 times. Now, the definition of a function is very similar to the definition of a relation. A function is a correspondence between 2 sets where each element in the first set, called the domain, corresponds to exactly 1 element in the second set, called the range. So the picture that I have up here, the issue with it is, for example, for 4 rubber bands, for this to represent this situation to represent a function where we could say that the drop distance is a function of the number of rubber bands, we would have had to have exactly one drop distance for 4 rubber bands, exactly one drop distance for 1 rubber band, exactly one drop distance for 2 rubber bands, and so on. An example of a function that we had discussed in class was if you go to like a froyo shop, and at a froyo shop you get your cup, you fill it with the whatever flavor froyo you want or flavors you want, you put toppings on if you want, and then in order to determine how much you pay, you weigh the froyo cup. So each weight ends up corresponding to exactly one price that you pay. So in that example, the first set, the domain, would be the weight of your froyo cup, or of your froyo. And the range would end up being how much money you pay. So you can say the price in dollars. So for example, let's say they charge 50 cents per ounce. Like 1 ounce would correspond to 50 cents. 2 ounces would correspond to $1. 3 ounces would correspond to $1.50, and so on. And like if you had 4.5 ounces, you figure out how much that would cost. But basically, every weight ends up corresponding to exactly one price. Every element in the domain corresponds to exactly one element in the range. So all functions are relations, however, not all relations are functions. So for determining whether a relation is a function, we can look at these sets of ordered pairs. And you just have to think about the definition. We want basically every x value to correspond to exactly one y value. So looking at this first set, okay, we have -3, 2, 3, and 6 for the x values. Usually, sorry, I didn't say that before, but usually x is associated with the domain, and then the y is associated with the range. So in this first set, we have all different x values, meaning that each of the x values will end up corresponding to exactly one y value. So we can say that, yes, this is a function. Yay. Okay, the next set, let's see. Oh, well, we end up having the x value of 2 occur twice, and that x value of 2 ends up corresponding to 2 different y values. So we have the point 2, 4, and then the point 2, 2. So the x value of 2 corresponds to 4 and then also corresponds to 2. So this is not a function. It's a relation, but not a function. And the last set of ordered pairs that we have here, the x values are times, it looks like, and then the y values are temperatures. And it looks like that each time corresponds to a different temperature, or each time corresponds to exactly one temperature. So this is a function. All right, there's different representations of functions. So you can represent functions numerically, so like as a chart or a table of values, graphically, verbally, like describing the function, kind of like my froyo example, and then algebraically with a mathematical model or an equation. So we're going to first talk about functions defined by equation. So typically a function represented by equation uses the x and y variables. And part of the reason for that is so that we can also represent equations of functions graphically in the xy plane. So x can be any number in the domain and is referred to as the independent variable, and y depends on what value of x is selected and is referred to as the dependent variable. Okay, so y is a function of x. If you think back to first semester, we actually studied a type of function. We studied linear functions, right? We were graphing lines from given the equation of a line. So whenever I give you the equation y equals to, I don't know, how about 2x minus 3, okay, you guys know that the graph of that equation is a line. But think about it, any real number you substitute in for x, then multiply by 2 and subtracting 3 is going to give you the y value that corresponds to that x value. So we can say that y depends on whatever the value of x is. And we can also say y is a function of x. Now it's important to remember that not all equations define functions. So these two equations here look very similar. However, one represents a function and one does not. So if I were to, over in this first equation, let x equal to 4, so I substitute 4 in for x to find y, I would get y is equal to 16. Okay, so that means that the point 4, 16 lies on the graph of y equals to x squared. But the x value 4 ended up having exactly one y value. Over in this other equation, if I also let x equal to 4, okay, well then we look, well what is y equal to? Well, this is a constant equals to y squared. So if you think about solving for y using square root method, this would be y equals to plus or minus the square root of 4, or y equals to plus or minus 2. So the x value of 4 ends up corresponding to y equals to negative 2 and y equals to positive 2. So that means that the graph of x equals to y squared actually has the point 4, negative 2 and 4, positive 2. Okay, the x value 4 actually corresponded to two different y values. So this first equation represents a function, and then this second equation does not represent a function. They look very similar, but one is just a relation, and one is both a relation and a function. Okay, so functions can also be represented graphically in the Cartesian or the xy plane. And for the graph to represent a function, it must pass something called the vertical line test. And the vertical line test really just goes back to the definition of a function. So given the graph of an equation, if any vertical line that can be drawn intersects the graph at no more than one point, the equation and graph defines y as a function of x. So I want to go back to those two equations. Actually, I want to adjust this definition for vertical line test first, actually. So how about just given the graph, given a graph, okay, it doesn't have to be of an equation. You don't have to know what the equation is. But given a graph, if any vertical line that can be drawn intersects the graph at no more than one point, then the graph defines y as a function of x. Okay, that's better. But let's go back to those two equations that we were looking at before. So we had y equals to x squared, and then we also had x equals to y squared. The graph of y equals to x squared we'll be examining soon, but it actually looks like this. Kind of a U shape, okay? And remember we said when x was equal to 4, y was equal to 16. Okay, the point, you had the point 4 comma 16 on the graph. Whereas for x equals to y squared, that graph is actually like a sideways looking U. Where when x was equal to 4, y was equal to positive 2, and y was equal to negative 2. So there were actually 2 points on the graph that corresponded to x equals to 4. So looking at the first graph over here in blue, you could imagine that any vertical line that you were to draw, okay, would intersect the graph at exactly 1 point. However, over here, the green graph, the graph of x equals to y squared, if we were to draw a vertical line, say through x equals to 4, it would actually end up intersecting the graph at 2 places, okay? Therefore, failing the vertical line test. This graph over here fails the vertical line test. This guy passes the vertical line test, and then this graph would fail the vertical line test because there are vertical lines that you could draw that would intersect the graph in more than one place. Therefore, function, not a function. All right, looking at these graphs, this is just the graph of a line. A line will always pass the vertical line test. Therefore, function. Okay, circle. I can draw a vertical line that would end up hitting the graph in more than one place, so fails the vertical line test, not a function. This is similar to the graph that I had above. Fails the vertical line test, not a function. Okay, this one I probably shouldn't have put on here. This actually does pass the vertical line test. The equation of this graph is actually y equals to 1 over x. We're looking at that equation. You can think any real number that you substitute in for x, you're going to get exactly one y value. So this is a function. All right, function notation. So the symbol that we have here is read f evaluated at x or f of x, and represents the y value that corresponds to a particular x value. So basically, y and f of x are interchangeable. Now, it's really important to remember that f of x does not mean f times x, okay? Really, function notation is a naming tool for functions. So if you're dealing with multiple functions, you can name them different letters. The most common function names are lowercase f and capital F, which represent different functions. Lowercase letters represent different functions from capital letters. But really, most any other letter can be used. And their common function names are like lowercase g, capital G, lowercase h, capital H, p, lowercase p, capital P, and so on. Now, the letter most commonly used for the independent variable is x, but really any letter can be used. Another common variable for the independent variable is using t, right? So like if t represents time, t is commonly used. So although we think of y and f of x as interchangeable, the function notation is useful when we want to consider, oh, I said this, two or more functions of the same independent variable, or when we want to evaluate a function at more than one argument. So here's the equation of a line, but instead of having y equals to negative 1/2 x plus 5, we have f of x equals to negative 1/2 x plus 5. So this is the function f. We can call it the function f. Now if we want to find f of 2, what this is saying is we want to find the y that corresponds to x equals to 2. So the way that we do this is we have f of 2, and we're just substituting 2 in for x. So that's negative 1 plus 5. Okay, so f of 2 is going to be equal to 4. So that means that the point 2, 4 is a point that lies on the graph of f. So another piece of information I probably should have added up here is that x, y, the ordered pairs that represent points on the graph of a function, can also be thought of as x, f of x, or g of x, h of x, whatever the function name is. Okay, so if we want to find f of negative 1, we're just substituting negative 1 in for x, and then we can simplify. So that's positive 1/2 plus 5 will end up being 11/2. So negative 1, 11/2 is a point that lies on the graph of f. Okay, so if we want to find f of 2, here I can just use this f of 2. I'm just going to substitute 2 in for x. Oops. Make sure you are using parentheses when you are substituting values in. That's negative 8 plus 12 minus 12 plus 12. So f of 2 equals to 4. So 2, 4 is a point that lies on the graph of negative x cubed plus 3x squared minus 6x plus 12, graph of f. Okay, f of negative 1. Okay, negative 1 cubed is negative 1 times negative 1 will just be 1 plus 3 plus 6 plus 12. So is that 22? So f of negative 1 equals to 22. The y value that goes with x equals to negative 1 for this function is 22. Okay, you can do the u-try. All right, so we're going to look at this graph. Now this graph is the graph of g, or g of x. Its name is g. So if we want to find g of 0, that means that we're going to go to x equals to 0. And we're going to find the point on the graph where x equals to 0, and we can see that that point's right there. And that point is 0, negative 4. So that means that g of 0 is going to be equal to negative 4. The y value that goes with x equals to 0 is negative 4. Okay, to find g of 2, we'll go to x equals to 2. Oh, that's easy to find on the graph. That point is 2, 0. So g of 2 is going to be equal to 0. g of negative 1, we go to x equals to negative 1 and find the point that corresponds on the graph. That point is negative 1 comma negative 3. So g of negative 1 will be equal to negative 3. Part D, so find x such that g of x equals to negative 3. For A, B, and C, we were actually given the x values and we're being asked to find y. In part D, we're given y and being asked to find x. So I'm going to go down to negative 3. Oh, one of the points is already found. Okay, there are 2 points where y, such that y is equal to negative 3 on this graph. So this point is 1 comma negative 3, and we have the point negative 1, negative 3. So for x such that g of x is negative 3, we'll have x equals to negative 1 and x equals to positive 1. Okay, so there's 2 different types of domains that a function can have. So an implicit domain is the largest set of real numbers for which a function is defined in the output value of f of x as a real number. So for example, we already looked at y equals to x squared represents a function. The largest set of real numbers for which this function is defined is actually all real numbers. You can substitute any real number in for x and you will get a y value. So the domain here, the implicit domain, is all real numbers. Should say implicit domain. It's the domain that doesn't need to be stated because it's the largest possible domain. Now an explicit domain is a domain that's clearly stated for the function that restricts the implicit domain. Let's say that for that same function, that x represented time. Well, time can't ever be negative. So what if we explicitly stated this domain? We restricted that function's implicit domain to be x has to be greater than or equal to 0. Okay, so here f of x equals negative 5x plus 1. That's a linear function, right? The graph of that equation is a line, and we know that lines are defined for all real numbers. Their implicit domain is all real numbers. Well, we want to evaluate this function for the domain that's stated here. Okay, so only for these x values. So we want to find f of negative 1, f of 0, f of 2, and f of 3. So negative 5 times negative 1 plus 1, that's going to be 6. Negative 5 times 0 plus 1 will be 1. Negative 9. Negative 14. So this domain that's stated here has a range of 6, 1, negative 9, negative 14. Okay, those are all the y values that go with the x values in that domain. If I were to go back to the pictures that I was drawing before. So if this is our domain, X is the variable in our range. Okay. Or I could call it f of x. Okay. -1 ended up corresponding to 6. 0 corresponded to 1. -9, sorry, no. 2 corresponded to -9. And 3 corresponded to -14. Okay. So that's just a little introduction to functions. You'll study them again in Algebra 2, in pre-calculus, in calculus, and it's also a little introduction to function notation, which we will continue to use this year.